All right, so electric charge and electric field. We want to move into a new world now. It's pretty exciting. So you've experienced static electricity somewhere in your life. You rub a balloon on your head and you stick it to the ceiling. You've scuffed your feet across the carpet and zapped someone. All sorts of things with static electricity. Benjamin Franklin demonstrated that lightning was related to static electricity. He made a connection that is now part of the evidence that all directly experienced forces except gravitational force are manifestations of the electromagnetic force. How about that one? That's a weird one, huh? So all directly experienced forces, so I place my hand on the table and my hand doesn't move through the table. Why? Because the electrons in my hand are being repelled by the electrons that are making up the matter in the table, and the protons in my hand are being repelled by the protons that are making up the matter in the table. It's wild stuff, people. So we're going to be talking about force fields and all sorts of things that sound crazy science fiction-y. Borneo amber. Turns out that if you take some amber and you're like, hey, wow, this is pretty cool. I want to polish this to make it look nice. And then it attracts little things. You're like, hey, what's going on? That was how we discovered this idea of static electricity. So the word for amber is electron, and that's how this all got started. So matter is made up of protons, neutrons, and electrons. And no matter what they tell you in chemistry class, neutrons have mass, electrons have mass, and protons have mass. They all have mass. So protons and neutrons are all pretty close to the same mass. Not quite exactly there, but in chemistry you say they each have a mass of 1. And then we say electrons have a mass of 0, but they don't. They have mass, 9.11 times 10 to the negative 31st kilograms. So if it exists, if it's matter, it has mass, and electrons have mass as well. Our inaccurate but functional idea of what an atom looks like, we have the protons and neutrons here in the nucleus, and then this electron cloud, which can look all kinds of different kinds of scientific-y fun orbits with the electrons orbiting the electron cloud. The electrons are generally far apart from the nucleus, and most of the mass of any atom is located inside the nucleus. The other thing that we have to talk about is that protons have positive charge, electrons have negative charge, and the magnitude of that charge is 1.6 times 10 to the negative 19th coulombs. Coulombs is our new unit here. It's the unit for charge. It's how much charge a proton or an electron has. And what we can do is say, okay, in nature, atoms are normally found with equal numbers of protons and electrons. So all those positives and negatives, 1.6 times 10 to the negative 19th coulombs, balance out, and we have something that is called electrically neutral. But if we add or remove electrons from matter, it will acquire a net electric charge with a magnitude equal to E times the number of electrons added or removed. Important point right now. Electrons are added or removed. Electrons are generally far apart from the nucleus. If I take away electrons from something that was initially electrically balanced, then if I take away an electron, I leave behind a positive charge. If I add extra electrons, then I have something that will have a net negative charge. If I reach into the nucleus and I take away a proton, I've done a nuclear reaction. It will not be stable. It will be radioactive. I may cause a large explosion. You do not add and remove protons. If you add and remove protons, you change what something is. If you look at the periodic table and you talk about what nitrogen is versus what oxygen is, your definition there is based on the number of protons in the nucleus. That's what matter fundamentally is. If you go reaching in and changing the number of protons, you're changing what it is, and we call that radioactive decay. So we're not doing that. So please, don't tell me that you added a proton to something or removed a proton, because that would be so very wrong. So we're going to add or remove electrons. So how many electrons are there in 1 coulomb of negative charge? Well, to get all the way up to 1 coulomb, so Q equals N, the number of electrons, times E, the charge per electron. N equals Q over E. 1 coulomb divided by 1.6 times 10 to the negative 19th coulombs per electron is 6.25 times 10 to the 18th. So huge number of electrons to get to 1 coulomb. Alright, so it turns out that it's possible to transfer electric charge from one place to another. The body that loses electrons has an excess of positive charge, while the body that gains electrons has an excess of negative charge. All we're doing is temporarily separating the charges. We're not doing anything fundamental to the states of matter. We're just doing this temporary separation of charge. Everything will eventually come out to be electrically neutral again. So we do this when we scuff our feet on the carpet. So here's my PhET simulation of John Travoltage. I hope this isn't too loud, but John's here and he's scuffing his feet on the carpet and he's building up electrons in his body. He's getting a net negative charge. And then when he touches the doorknob, and then we can do it a lot. So this is a PhET simulation, but I can't think of any good reason to do this simulation other than a fun example of electrocuting. Oh, had a big reach. I'm going to do it up at his nose and build up more charge. I don't think he gets much louder when you build up a lot of electrons. But you do this, right? You scuff your feet across the carpet and then touch your friend's ear and zap them. If you don't do that, you should, even though it's a bad thing to do. Alright, so there's John Travoltage. That was fun. Alright, so the body that loses electrons has an excess negative charge, so when he scuffed his feet on the floor, the carpet lost some electrons to him, and then when he touched the doorknob, providing an escape route for those extra electrons, they flowed out of his finger into the doorknob, and the doorknob would eventually balance out with the carpet and everything would be electrically neutral again. Because we have the law of conservation of electric charge. During any process, so far as we can tell in the universe, during any process, the net electric charge of an isolated system remains constant. It is conserved. So we can have a temporary imbalance. I take my ebonite rod and rub it against animal fur, and I will build up extra electrons on the rod, taking some electrons temporarily away from the animal fur, but shortly thereafter those excess electrons will escape the rod and the animal fur will gain more electrons and become electrically neutral once again. Alright, this is not relationship advice, but opposites attract and likes repel. You've heard this, right? So if I have a temporary imbalance of charges and I have a net positive on one object, so these are like little styrofoam balls connected by a string. Maybe they're styrofoam balls wrapped in aluminum foil. So they don't have much mass, so we're not too worried about gravitational forces pulling them down. And there's just positive charge on one and negative charge on the other. We'll find that they are attracted to each other. If I have two negative charges, they're repelled from each other. Two positive charges, they are repelled from each other. We use this in all sorts of applications, that if you can just have a little imbalance of charges. So when you go to the gas station and pump your gas, you have this liquid crystal display. This liquid crystal display is taking these liquid crystals and lining them up in such a way that you can read the numbers flashing by as you pump gas into your car. And so what you're seeing is these manipulated pixels of these crystals, and they're manipulated into place by positive and negative charges. All right, so not only can electric charge exist on an object, but it can also move through an object. Substances that readily conduct electric charge are called electrical conductors. Materials that conduct electric charge poorly are called electrical insulators. Very similar to what we were talking about earlier in terms of thermal conductors and thermal insulators. In fact, many of the same objects are good thermal conductors and good electrical conductors, metals, and something that's a poor thermal conductor is frequently a poor electrical conductor, like air. You can charge by contact. You build up charge on your ebonite rod by rubbing it on the bunny fur, and then you touch it to a metal sphere, and it leaves the rod and goes into the metal sphere, and I've charged this metal sphere by contact, by actually touching it with something that had an excess of negative charges. I can also charge by induction. So I can hold my my ebonite rod up close to my sphere. The electrons that are already part of the sphere will be repelled, because likes repel. So they'll be repelled from that excess of negative charge, leaving behind the positive charges. And then I'll provide an escape route. I'll just touch the far side of the sphere with a grounding wire, and all of these electrons are like, hey, there's a whole bunch of us here, we're kind of crowded. Some of them will escape through the grounding wire. Then I take the grounding wire off, I take my source of negative field away, and I'm left behind with a net positive charge. So I took a negatively charged rod and I created a positively charged object. So that's a weird thing, and I did that by inducing that to happen, charging by induction. We do that by way of this thing that we call polarity. So if we want to polarize something, I hold negative charges in the area, and things that are paired up, positive and negative, the positive is attracted to this negative field, the negative is repelled, and I have polarized area. All right, so this is going to bring us to Coulomb's law, which, when we said that likes repel and opposites attract, the repel and attract is a force, and that force has a value. It's going to involve some crazy math, but it's still got a number. So Coulomb's law states that the magnitude of the electrostatic force exerted by one point charge on another point charge, and a point charge is just saying, I don't care how big this charge is, I don't care if it's a ping pong ball coated in aluminum foil, or if it's a tiny thing or a huge thing. I'm just going to pretend that it's just a point in space that has an electric charge separated by some distance r. The magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the magnitude of the charges. So bigger charges, bigger force, and inversely proportional to the square of the distance. So this is an inverse square law. We saw this already with Newton's law of universal gravitation, a case where the further apart objects are, the less influence they have on each other. That is the case here as well, and that that diminishing force is exponential. It's inverse of the square of the separation distance. But force equals K. K is a number. It's going to be 8.99, or maybe we'll just do 9 times 10 to the 9th Newton meters squared per coulomb squared, times Q1, Q2. So these are charges. So if it's 1 proton and 1 electron, then each of those is 1.6 times 10 to the negative 19th coulombs, divided by the distance that they're separated squared. Now remember, coulombs is just coulombs, but K here, our constant, has units of meters involved. So we're going to have to take whatever our separation distance is, convert it into meters, and then square that number. We can have our coulombs constant, our coulomb force, be responsible for providing centripetal force. So in our... Sorry, my dog's barking. Hold on. Sheena, hey pup. In the Bohr model of a hydrogen atom, the electron is in orbit about the nuclear proton at a radius of 5.29 times 10 to the negative 11th meters. Determine the speed of the electron, assuming the orbit to be circular. So it's providing centripetal force, so we can figure this out because say the force equals K Q1 Q2 over R squared. So we have R, we can square it. We have a proton and an electron, so we have Q1 Q2. We have K. We can figure out the force. It's pretty cool. And it turns out that it's a substantial force, and if we then say that force is the centripetal force, force equals mv squared over r, and we have m and we have r, we can figure out the velocity of the electron orbiting the nucleus, and it turns out that it's wicked fast, 2.18 times 10 to the 6 meters per second, a significant fraction of the speed of light, which is the ultimate speed limit. So this is really neat stuff that we're approaching here as we study this. Remember when we talked about net force in Physics 1? Net force is, if we're talking about something that's happening in the y-axis, we'll say the net force in the y-axis is force up minus force down. Net force in the x-axis is force to the left minus force to the right, or vice versa. So we do this adding together forces on a line. So if I have 3 charges here and I want to figure out the force that is being experienced by charge number 1, I would figure out the force that exists between charge 1 and charge 2. And so force equals K Q1 Q2 over R squared. And then I would do the force that experienced by charge 1 due to charge 3. Force equals K Q1 Q3 divided by R squared. And I would figure out the net force. Micro is 10 to the negative 6 coulombs here. So positive 3 times 10 to the negative 6 coulombs is the charge on charge number 1. That's a typical range for electrostatic charges. So if micro isn't in your lexicon right now, you should get it in there. It's times 10 to the negative 6th. Alright, so if we wanted to figure out these charges, so we do the force between Q1 and Q2, get 2.7 newtons. The force between charge 1 and charge 3, we get 8.4 newtons. The net force then is going to be, adding them together, this one was in the negative x-axis the way we had it depicted, so negative 2.7 plus positive 8.4 gives us a net force of positive 5.7 newtons. If you can do it in one dimension, you can do it in 2, and you can do the vector sum, a squared plus b squared equals c squared, all of that stuff from Physics 1. It still exists. All right. So test charges, we're going to get into the world of force fields. In the world of force fields, what we're going to do is explore what's going on at a point in space instead of with a charge like so, with just a single test charge somewhere in space. So here's my positive test charge. I'm going to stick it here, and I'm going to see what kind of field, what kind of charge it would experience. So we have a positive test charge that has a magnitude of 3 times 10 to the negative 8th coulombs, and it's going to experience a force of 6 times 10 to the negative 8th newtons. So what we have is an electric field, newtons per coulomb, of 6 times 10 to the negative 8th newtons, the force, divided by 3 times 10 to the negative 8th coulombs, the charge. So newtons per coulomb. That is a force field that is being experienced. And then if we brought in a new charge, we could figure out what kind of force it would experience in that same space. That's the tool that we're building up to. The definition of an electric field is the force per unit charge, and it is units of newtons per coulomb. So the electric field that exists at a point is the electrostatic force experienced by a small test charge placed at that point divided by the charge itself. It is the surrounding charges that create the electric field at a given point. I guess you probably would have guessed that. So skipping ahead, and we can do this in terms of vectors as well, but we're not going to worry about that right at the moment. Turns out the electric field does not depend on the test charge, so we can talk about a point charge and say the electric field equals kq over r squared, and come up with a value for electric field that will be independent of making up some nominal value for the test charge. We'll use this kind of thing. We're going to build up to parallel plate capacitors when we actually use them in electric circuits, but a parallel plate capacitor is an area where I have a metal grid with a bunch of positive charges on one side, a bunch of negative charges on the other side, and there's therefore an electric field that exists between the two plates of a parallel plate capacitor. If you noticed in this parallel plate capacitor, we drew some lines. They extended from the positive to the negative. Those are electric field lines. Electric field lines, sometimes called lines of force, would tell you if I took a positive charge and I stuck it here, where would it feel compelled to go? So if I took a positive charge and I placed it right here, it would follow this electric field line. Electric field lines start on positive charges, go away either toward negative charges or at least just away from the positive charge, or they go toward negative charges. Electric field lines represent the force that would be felt by a positive charge if placed in that spot. Electric field lines are always directed away from positive charges and toward negative charges. And here's a case where I have my parallel plate capacitor, and here in the middle here I have my nice parallel electric field lines, and then there's some weird edge effects when I get to the extremes here. But in the middle we have these nice parallel electric field lines. If I have 2 point charges in space, then my electric field lines would be more or less straight from the positive to the negative right there in this intersecting piece. But other places, initially if I placed a positive charge here, it would be mostly repelled from the positive charge. It wouldn't see the negative charge yet, so it would be repelled. And then as it moved away, it would start to sense the negative charge and it would be attracted to that. So that's how my positive test charge would behave inside this electric field. If I have two positive charges, then you can see that it's repelled from both. And if I stuck a positive charge right in the center of two other positive charges, it wouldn't know what the heck to do. So it would likely stay right there. It would be very unhappy. It would be in a region of high electric field, but it wouldn't have a good sense of which direction to go. You can draw all sorts of electric field lines, but sometimes they're wrong. There are three things wrong with part A of the drawing. What are they? Well, why are there 4 lines here and only 1 line there? The number of electric field lines that you draw is proportional to the charges involved. So here in part B we have this done correctly. And you'd have more field lines here. They wouldn't all be parallel here. All sorts of things are messed up about that. We don't need to talk about shielding. We're not going to build any conductors ourselves. I want to get to applications. So a standard photocopier is using electrostatics, a standard printer. What you do is you have this selenium coated drum. Selenium is photoconductive. So when you shine light through the thing that you're making a photocopy of, the white spots come out with some charges. I forget whether they're positive or negative. The dark spots come out with other charges. Well, now that you have this region of positive and negative charges, you can have the toner, which if you've ever gotten toner on yourself, it's just a bunch of black powder. It's kind of obnoxious. Well, you give that toner a little bit of electric charge, shoot it at the drum, it will stick to the oppositely charged particles. Now the drum rotates around on your piece of paper, and those black particles will stick to your paper. And then when you bake it on, and if you've ever noticed things coming out of a photocopier, they come out pretty hot. You bake it on and you've baked that toner onto the thing. And it's just by way of manipulating static electricity, that charged powder being attracted to the drum. You can do the same thing with laser printers and color printers and all that. It's the same process over and over again. With an inkjet printer, what you do is you charge up the ink and shoot it and deflect where it goes by way of charged plates, and you can spell out words by directing it in certain ways. All right, that's electrostatics and electric field. Good start. I'll try to shut this down.